Hi all, this is Sangeeta from ESP Engineering College, Karur. This lecture series is about fluid mechanics, and the course code of the subject is 23 CET 302. And the core objective of this subject is to introduce the students about properties and behavior of the fluids under static conditions, and to impart basic knowledge to the students through control and surface volume approach, and to expose the applications of the conservation of mass uh, to flow measurements and pipe flows. And the unit 1 goes with fluid properties and fluid statics, and we will be dealing with the four categories, that is foundations and frameworks and mechanics and applications. In foundations, we will be discussing about scope of fluid mechanics and definition of a fluid, and what are the methods of analysis and continuum hypothesis. And in the frameworks, we will be dealing with system and control volume approach and Reynolds transportation theorem. And in the mechanics, we will be dealing with the three subtopics, that is fluid properties, fluid statics, and manometers. And in application oriented, we will be dealing with buoyancy in floating bodies and stability of floating bodies. So these are the parameters which is has to be discussed in unit 1. And this slide gives you the information about the textbooks and the references which you can be used for this subject. And Modi, PN, and say the hydraulics and fluid mechanics, including hydraulic machines, and which is published by Standard Book House, New Delhi, and the edition is 2015. It's a primary knowledge-based textbook, and you have some references material, and you can also follow fluid mechanics by R.K. Banzol, and which also gives you the immense information regarding this subject. And stepping on to the next slide, this deals with the scope of fluid mechanics. That is, it is the branch of science which deals with the behavior of fluids at rest as well as in motion, that is at statics and as well as in dynamics. So fluid statics forces on pressure forces, stability, and buoyancy related, and fluid dynamics focus on momentum, velocity profiles for flow networks. And the diagram gives you the information related to this. And the next one is continuum hypothesis. The definition is by assuming a fluid and a continuous distribution of matter with no empty spaces, we can define properties like density and pressure at mathematically precise and at infinitesimal points. So this is related to continuum hypothesis definition. And in engineering scale, the continuum hypothesis holds good. That is flow of water in a pipe, that is pipe fluid flow, and where we can get with critical volume, that is the threshold of the continuum. And in that critical volume, we can analyze one single molecule, that is called as molecular approach. And with regards to the methods of fluid analysis, there are two major types of fluid analysis methods, that is Lagrangian approach and Eulerian method approach. And in Lagrangian approach, the focal point is related to a specific mass of particle, and the observer may be standing in a boat moving with the river current. And engineering applications for this approach is tracking the pollutant dispersion. Okay. So in Eulerian approach, it is a specific point in space. For example, standing on a bridge watching the river flow passed, and the application is measuring pipe discharges. So the mostly the civil engineering issues and practices the or utilizes Eulerian approach to design fixed infrastructure. And system and control volume approach. System approach and control volume approach. Tracking fixed identifiable mass as it moves and deforms. That is called as system approach. In a system, we are particularly locating some volume, that is called as control volume. So tracking a fixed region in space with respect to its mass and deformations is called as control volume approach. The figure gives you the highlights of both the approaches. And the next one is Reynolds transportation theorem, which bridges the gap between the Lagrangian method of analysis and Eulerian method of analysis. This Reynolds transport theorem allows engineers to apply foundational conservational laws, that is conservation of mass, to fixed spaces such as pipes, pumps, and channel flow. So it is explained as the system is a summation of time range of change of property within the control volume and net outward flux of the property across the control surface, whereas system is defined as the time rate of change of an extensive property within a system. So its major role is to bridge the Lagrangian and Eulerian method of analysis. And properties. There are some basic properties which we have to know when stepping into fluid mechanics in deep. The first one is mass density, which is denoted by the symbol called rho. The mass density is the foundational metric where all primary static properties or mathematical derivatives of the single concepts, that is from the mass density we can have specific weight, specific gravity, and specific volume. So when mass density is multiplied by gravity, that is g, that is denoted by a symbol called a w, which gives you the specific weight of a component. And the next one, when rho is divided by the dense rho of water, that is density of water, which gives you the value of specific gravity. Within the bracket we can denote it as S. And when we are taking the reciprocal of mass density, that is 1 by rho, which gives you the term called specific volume. So as we have seen in the previous slide, it is the ratio of mass to its volume called mass density, and its unit is kilogram per meter cube. And the specific weight is unit is Newton per meter cube, and the formula is weight by volume. And the specific gravity is dimensional, since it is the density of liquid to the density of water, and the specific volume unit is meter cube per kilogram, which is equal to volume per mass. And this slide gives you the details regarding the SI units. The next property, viscosity, is defined as the property of a fluid which offers resistance to the movement of one layer of the fluid over the adjacent layer of the fluid. And it also states that the shear stress on the fluid element layer is directly proportional to the rate of shear strain, and the moving plate moves with a velocity u, whereas the fixed plate has a velocity capital V is equal to 0. So the next one is fluid statics and manometry. In a static fluid, there are no shear stresses and the pressure acts purely normal to the surface. In manometers, utilize specific gravity and hydrostatic pressure gradients to measure pipe pressure differences in pipe networks. That is, delta P is equal to rho into GH, where rho is the density of the mercury, G is the gravity, and height is the height of the manometric fluid, that is mercury, from the datum line. There are different types of manometers, that is simple U-tube manometer, and the next one is inverted U-tube manometer, and the next one is differential manometer. So the next topic is buoyancy and flotation, and the core principle is a floating body experiences an upward force, that is buoyant force, which is equal to the weight of the fluid it displaces. There is two terms called weight, which is denoted by the symbol W, which represents the weight of the floating object, and buoyant force FB, that is called as upward force, which tends to move the object upward. Since these two forces are equal, the body or the object will be able to float. And in the engineering point of view, it is essential for the design of bridge pontoons, offshore platforms, and floating components. And the next one is stability of floating bodies. How a body is stably floating without sinking. And the concept is the restoring couple. When the metacenter, which is denoted by the symbol capital M, is above the center of gravity, capital G, the offshore forces, weight and buoyancy create a righting moment, pushing the structure back to equilibrium. We have seen about the buoyancy in the previous slide, that is, it is an upward force which resists or pushes the structure back to equilibrium, and M is the metacenter, and G is the gravitational force, and B is the center of buoyancy, and theta is the angle of inclination. And the critical point is that if M falls below G, the structure capsizes, that is, the structure uh, fails. That is, M denotes metacenter, and G denotes gravitational force. So the last slide gives you the overall framework of this unit, and first thing is defining the framework, that is continuum and control volume surface volume approach, and whether where we go with methods called Eulerian approach and Lagrangian approach. And next we have quantify the fluid, that is, we dealt with some basic terms, that is density, specific gravity, viscosity, specific weight likewise, and this it is applied to the infrastructure in terms of concepts related to manometry, buoyancy, and stability. So the fluid mechanics in civil engineering begins with preciously defining the physical properties of fluid and deploying geometric control volumes to predict its static and dynamic behavior across massive infrastructure. And the next lecture series, we will be dealing with Unit 2. Thank you.